Hello everyone. The title of this paper is The Effect of Impedance Control Stiffness to the Grasping Force for Different Objectives Check, prepared by me, Muhammad Syahmi bin Selamat, Dr. Ruhizaleza binti Ahmad Shauri and Ahmad Badiuzzzaman bin Roslan. In this modern era, there are various types of robot hand was built to improve human life. In order to make perfect object manipulation such as grasping and lifting, human-like robotic hand needs to be artificially intelligent and have the sense of touch in it. The capability to measure the force applied to the robot fingertip when in contact with object is the early stage of controlling the robot. The impedance control method is one of the many ways to control the robot hand. Impedance control is a dynamic control approach related to force and position. It is often used in application where the manipulators interacts with the environment such as robot hand and where the relationship of the force and position is concerned. The robot hand consists of one palm and 3 fingers. It made up with 7 degrees of freedom whereby each joint represents 1 degree of freedom. Each joint of finger is driven by a DC micromotor equipped with encoders. The encoders is attached to the motor to measure the rotation of the motor for position control of the robot hand joint. 6 axis force-stop sensors were located at the fingertip of the hand for a force measurement purpose in X, Y and Z direction. The system architecture using multiple PCI interface which are PCI NI 6225 and PCI Advantech. The function of this multiple PCI is to establish the interface between the hardware and software. Analog input block of a real-time Windows target in Simulink in host computer receive analog input from force-stop sensor. Digital input block in real-time Windows target in Simulink receive the signal from encoders and motor driver receive analog signal from Simulink both via PCI Advantech. The position-based impedance control was developed by considering the translational impedance equation to enforce an equivalent mass spring dashboard behavior for the position displacement when the end effector exerts a force on the environment. From the block diagram, the impedance control starts by setting the force reference Fref to its desired value. When the robot fingertip is in contact, it will produce external force. This external force only be taken from finger 1 because finger 1 is the main finger that control another finger as there is a short circuit between this finger. Not only that, only external force from finger 1 will be used in the impedance control system. When force external exceeds force reference, the position-based impedance control will be activated and it will modify the desired tip and position PD to PD new by using the impedance algorithm 1 and 2. MD, DD and KD are the impedance parameters known as mass, damping and stiffness parameters respectively. They can be used to produce the softness of the robot hand by changing the tip and position based on the force exerted to the robot fingers. If there is no force interaction occurring at the fingertip of the robot hand, PD will be equal to PD new. In order to implement impedance control, there are 3 impedance control dynamic parameters that need to be varied. From the experiment on the effect of varying impedance control dynamic parameters by Nasi, the graph below show force exerted to the fingertip while graph above show the modified position of the robot hand. Nasi conclude that MD and DD was set to 1 and 10 respectively as the graph show less fluctuate on modified position when applied to the fingertip. KD has shown the most influential parameter as graph shows when force external exceeds force reference, there is a significant difference on the modified position of the robot hand, which when KD increased by the factor of 10, the modified position becomes smaller. However, the work has not yet been done on a real object grasping. In the latest study, new 6-axis force-stop sensor has been used to replace the load cell sensor together with a new interface system for more accurate force measurement. However, the work has not yet been done on a real object grasping. Therefore, the objective of this work is to analyze the effect of varying impedance control stiffness parameter KD on the object grasping and the effect of grasping different object texture with the same impedance control stiffness parameter. This video shows how the grasping data taken. From the separate work, the 3-finger robot hand is tested for a real grasping on two objects. The tested objects in this experiment are bottle and ball, which have different texture. The texture of the bottle is hard, while the ball is very soft or spongy. It starts by varying the impedance control stiffness parameter for both ball and bottle. Firstly, the impedance control stiffness parameter is set to KD 1000. Force reference value FREF was set at 0.1 Newton. The 3-fingered robot hand was tested for grasping a plastic bottle and a sponge ball as shown in the figure. The external force measured by force torque sensor in figure 1, namely force external 0, is collected at 0.25 seconds after the fingers start to touch the object. When the grasping tightens at 1 second after the first touch, the external force, namely force external 1, is collected. Force rate data was taken by using this formula. In other words, force rate shows the intensity of the force applied to the robot fingertip when in contact with the object. The procedure was repeated 25 times for each object. After completed, similar procedure taken for another impedance control stiffness parameter value, which are KD 500 and KD 250. In this work, analyzation of F-rate data was done to analyze the effect of varying impedance control stiffness parameter on two objects grasping. The F-rate data will undergo pre-processing step, that's it, normalization. Normalization is the process of scaling an attribute data so that it falls within a narrower range, which is from 0 to 1. Figure 1 shows the F-rate before and after normalization. Histogram chart has been used to show the frequency for the range of F-rate. Line chart is used to compare the F-rate data for grasping bottle and ball. All of this was done to look for the effect of varying KD on F-rate and the range of F-rate for bottle and ball. This graph shows the distribution of F-rate after normalization. From the analysis, there is no pattern of data that can be seen from figure A, B, C, and D. However, the stiffness at 1000 has shown the most significant difference of force rate for both object grasping. Besides, at the same stiffness, the force rate data are most frequent in the range of 0 to 0.2 for ball, compared to 0.2 to 0.4 for bottle. Thus, it can be concluded that the grasping force rate for bottle is higher than a ball. Figure on the left shows the force rate measurement of grasping for different KD. Based on this figure, it also shows the same result with previous histogram graph where the F-rate of grasping bottle is higher than grasping ball for every varied KD. However, the measured value sometimes does not precise because there was a backlash occur. This backlash was due to inaccurate measurement of sensor as there is small position error occurring on the gear of the robot hand. This figure shows the force rate measurement of grasping for different object texture. The result shows consistent reading of force rate in the range of 0 to 0.4 for ball grasping after 11 data. This indicates that when the connection between the hardware components changed after 11 experiment, the effect of the narrative factor from the friction between gears, bearing, and connector shaft to the force measurement started to reduce. But it is different for data when the robot hand grasping a bottle. There are no patterns shown from the graph. However, we can conclude that the average of force rate in the range of 0.2 to 0.7. As a recommendation, more grasping data required in order to analyze the effect of force rate to the object texture.
For a conclusion, an intelligent robot hand needs to adjust the stiffness of the joints by determining the suitable stiffness parameter value by itself. Prior to this, the effect of varying impedance stiffness parameter KD on the measured force when grasping object with different texture has been observed in this work. KD 1000 showed the most significant difference of force rate for the two objects compared to other stiffness values. At the same time, the force rate data are mostly measured in the range of 0 to 0.2 for ball compared to the higher range of 0.21 to 0.4 water bottle, by 48% and 40% from the total number of experiments respectively. From the most frequent range of the force rate, the average value for bottle is found higher than the ball. The analysis results show that the force rate is feasible parameter for developing an intelligent object recognition method in the future. Thank you.